In the previous video, we looked at the fact that if we determine our shear stress distribution from shear flow, we didn't have a huge difference between our assumption for thin wall sections and assumption for thick wall sections, particularly if we're looking at the web. And I had said at the end of that video that, well, why do we bother with this shear flow? And it really comes down to the resultant forces. Rather than the stresses are what's the more important thing. So I wanted to try to illustrate that here. So I've redrawn sort of the shear flow distribution for a generic I section. So if we have this applied load V, well, we're going to have some shear flow going up in the web, and then flowing out and flowing in. And so if we want to draw this as, so this is our shear flow. Remember, this is going to be shear per unit length. Well, what if we redraw this as a as forces? And remember that we can we can get there by integrating. So if we look at our forces, we'll do a similar sort of stick drawing. Well, we're going to have some VF coming in, some force V of the web going up, and some force VF going out. In fact, let's just try to, and then keep in mind that this force in the web is acting right in the middle of the web, and then we have some V coming down. And how we get from here to here, say if we look at, say, the flange, so, VF and VW can be determined by integrating the shear flow distribution. We'll just, so for example, in the flange, say we've got, some distance B over 2, and we have some shear flow QA, and say this is just in the flange here. So V of the flange, integrating is really just taking the area under this curve. That's just going to equal 1/2 QA times B over 2. So we won't work through that numerically. You can do that on your own, but I just want to kind of show you how we get from here to here. What I am more interested in is having a look at what these forces are doing to the section, because we've got some forces going vertical, some going horizontal. We've got some which are they off center from the load or not, and so we've got a free body diagram here. We want to kind of see what's going on with that. So let's just start by summing the forces in the vertical. So some of the forces in the Y, we can see that the applied load is going to have to equal the shear in the web. So V sub W equals V. So web shear equals the applied shear. This is, as a side note, this is an even better support for our assumption that when we're dealing with an I section, we can just look at our applied shear over the determine shear stress, we can look at just the web as the contributor to that. Well, let's sum our forces in the X. And that's going to equal 0. We have 2F going to the left, 2v sub f, minus 2 of them going to the right. And that equals 0. So we see we have 0 equals 0, all of the v sub f being the same. So that's not overly helpful or overly surprising. So let's sum the forces, sum of the moments at the centroid. And that equals 0. And again, our centroid, we're going to have some distance, d over 2, d over 2. So let's work that out. So you have our applied load, v, times 0 distance from the centroid. Again, similar with v sub w. It's acting right in the middle. I've just drawn it just to the right for clarity. And then we have plus v sub f times 2 df. We have 1, 2 of those. So that way and that way. So plus 2 times v sub f times d over 2. And we have 2, so if we right-hand rule, so if we have 2 here and here, pushing us this way, this one and this one are pulling us back. So 2 v sub f times d over 2. And all of that has to equal 0. Well, those go to 0, and that equals 0. So 0 equals 0. Again, failed section is in equilibrium. So again, you say, well, Lucas, you still haven't really convinced me what the shear flow stuff is all about. I don't really see the fuss over it. Well, you know, for an I section, it's like, okay, we found the stresses weren't that different. We found that you said, oh, the key's really when we're going to start looking at forces. And again, it's like, well, everything's together. We can kind of see that we can go from, you know, a shear flow to a force, but that's just integrating. That's nothing really new. Still don't really know why we learned all the shear flow stuff. Well, bear with me. Let's look at a different section. So we saw for an I section, didn't really matter. Let's look at a box section. So the shear flow for a box section, I'm just going to draw it out here. And we've not worked through an example on this, but we can use our rules about our horizontal and our vertical distribution to really be able to see. So we know that our vertical pieces have to have a parabolic distribution. And we know that the middle one have to have a horizontal. And we know that we have to have equilibrium in the at a corner. You know, for those equal and opposite forces have to be able to flow through there. And so what we find is that right at the center, Q equals 0. And it's really based on symmetry. And I'll just draw this over. And so we get a shear flow distribution that looks like, draw that a little bit more parabolic, that looks like this. Where call that QA, that's going to equal QA. These two are both equal, and again, apologies on this side, not the best distribution drawing, but our shear flow will go out like that. So that's our shear flow, and it's, you know, the big key that I want to show is it's going to be 0 right here. Now I've drawn it flowing sort of down and out because it's a better way to visualize it. But just remember that, you know, on the opposite, just if this was a box coming out, just on the other cut here, we've got an equal and opposite force going up, and so that's why, you know, sometimes you'll see I'll flip the directions I point the arrows, but they are equivalent. But say we want to look at, you know, what our distribution of forces are, just like we did here for the I section. So if we put ourselves some coordinates in, y, x, here's our box again. And that's our centroid. Well, we've got a force. Like I said, we'll draw our applied load. V coming down. So I'm just going to swap the forces here just to make it look a little bit cleaner. But like I said, these are just equal and opposite. You think about it, just on the other side of the cut. So I hope that doesn't confuse anyone through there. And then we've got our V sub W, V sub W, VF, VF, and that's going to be our distance, B over 2, B over 2, and then a distance, D over 2, D over 2. And again, the only way that we would go to find the magnitudes of these, if we're going to work this example out numerically, would just be to integrate. So like for this VF here, it's just the area under the curve from the centroid to B over 2 times QA divided by 2. So just like we did up here. And then the magnitudes of V sub W, well, we can do it, we can either find the profile of our vertical shear stress distribution and integrate that over the height, or we can kind of do a shortcut. For example, like for an I section, we know that there's only, because we've got to be in equilibrium, so we can either work out what this is, integrate underneath there, or we can just see, well, that's the only force in the vertical direction, so it has to be pointing up. We'll do a similar thing on the box section because, you know, they're equidistant. Well, we know that they're going to be, by symmetry, we know they're going to be the same. So let's sum our forces in the y. And we get, you know, minus v plus 2 v sub w equals 0. And we see that v sub w equals v over 2. And that makes sense from everything we know from doing statics with simply supported beams with a point load in the middle. This is just symmetry is working out for us. Well, let's sum our forces in the x. And that equals 0. And we have, you know, 2 flange forces pointing to the right and 2 pointing to the left. So we have 2 v sub f minus 2 v sub f equals 0. So 0 equals 0. They're, from symmetry, we can work out, these areas and these distances are all the same. These magnitudes are all the same, so these forces are going to be the same. So everything's just going to cancel there. So let's look at at the moment. And that equals 0. So we have our, and this is where, we're going to see something maybe a little bit different. So on the I section, well, we've got equal and opposite forces in the flanges, but then we had the, our applied shear load and our applied, and our shear flow in the vertical direction. Well, that was all centric. Well, now we've got, as we come to a box section, we've got some distance here. Well, let's see if there's any difference which is going to occur, and find out if that is this section still in equilibrium. So you've got v times 0 plus we've got a v sub w times b over 2 minus v sub w times b over 2. Then we have 2 of the flange shears trying to spin it positively. So you've got plus 2 times v sub f times d over 2 minus 2 times v sub f times d over 2, and that equals 0. And we work all of that out, and we see that, 0 equals 0. So the section is in equilibrium. All right, well, that's 2 different sections now, Lucas, that you showed, and seen that, really there doesn't seem to be a huge difference going on. So yeah, we go from shear flow to sort of forces in there, and we find everything's stable. So that in itself, the fact that it's stable, the fact that there's no unbalance in force is important. So where if we've got these nice symmetric sections and we're loading in their principal axes, well, they're just going to behave with, sort of some predictable shear flows going through. Well, what about if we look at an asymmetric section? What if we look at a channel? So our I'll draw the shear flow distribution first. So we've got to start at 0, and we're going to come up linearly from the edge. And that'll be QA. And then we will vary parabolically within the web, the vertical member. So this is just us going through following our rules that we learned when we're trying to determine shear flow. And then we're going to flow around, pretend like, we're putting water in here. Well, it's going to want to flow around like that. So it's similar to, if we're going to put water in, here we're sort of pumping up, where we're putting in from the ends. It's going to fill up here and it's going to spill out there. Same thing here, putting it in the middle, and it's going to flow down and float around. So that's why we call it shear flow. Anyways, so that's what our shear flow looks like in a channel Well, let's look at the forces. And again, we're not doing this with any numbers. We're just going to work through really on sort of what we would see in terms of just a general. So our centroid's going to be somewhere floating in here. And we'll say that that's some distance x from the center of the web. And we'll put our coordinate system up here, x, y, and we have our applied shear force, V. Well, and like I say, I'm just going to reverse this just for the shear flow. V sub F, V sub F, and I'm just going to try to draw, well, we'll draw it just to the other side, V sub W. D over 2. All right, well, let's work through our and this is our forces in the section. All right, well, let's work this out and kind of find out, well, what do we get here? So let's go. Sum of the forces in the y equals 0. Well, V equals V sub W. That's what we found previously. Nothing new there. Sum of the forces in the x equals 0. Well, you have VF minus VF equals 0. Again, nothing terribly exciting with that. Well, let's go. Let's sum forces, some moments about the centroid. All right, so what do we get? We have V times X going in the positive direction. So V times X. And then we have minus V sub W times X, again looking fairly boring here. Then we have a minus V sub W, V sub F, sorry, times D over 2. And then we have another minus V sub F times D over 2, and that all equals 0. Well, these two cancel because V sub W equals V. And we're left with, we've got two of these, so we're left with V sub F times D. Well, that doesn't equal 0. The section isn't in equilibrium. You know, this is holy smoke. This is we finally have something interesting. Why we bother to look at all of the shear flow stuff in the first place is really for these asymmetric sections. What this is saying that if we load a just the shear force here, well, we have this unbalanced moment. So what that means is that a moment is generated, and in order to keep the section in equilibrium, this moment has to occur. A moment of positive VF times D. Well, basically if the section won't twist. So in essence, if we're going to push down right on the web, well, then we so say we have our channel here. So if we're pushing down on the web, what's going to happen is, I'll draw it in red, is basically the section will bend. So that's our original one. The section is going to both bend and twist. That's crazy. And that's all just simply because of this shear flow. Well, we, as structural engineers, we like symmetry, and we like things not to bend and twist on us. So how do we counteract this? Well, really, you go like, well, Lucas, look, on these others, you loaded through the centroid. Maybe that's your problem. Well, if we load through the centroid, well, it actually gets even worse. So we've got a moment generated, spinning in this direction, sort of clockwise from our flanges. If we put our load in the centroid, well, there's also an additional clockwise movement just from the shear flow of the web. So it gets even worse loading through the centroid. So if we want to try to counterbalance the load, well, we actually have to load out over here. And so let's just work that out really quick. So stop the twist. Load outside of the section. So we'll draw our section again here. So we need to load some distance E up here. And again, I'll just draw our forces really quick. V sub W, V sub F, V sub F, and again, this is going to be D over 2. D over 2. We already know the forces are in equilibrium, so let's look just at the moment. And I'm just going to call this point here O. Sum of the moments at O equals 0. So that way we can just sort of cancel out our shear. So we have our applied shear times 0 distance. Then we have plus V sub W times E minus 2 times V sub F times D over 2 equal to 0. That goes to 0. We get V sub W times E equals VF times D. So we find out that E equals V sub F times D over V sub W, but because these two are the same, E equals V sub F times D over V. So that means that in order to keep this thing from twisting, we have to load out some distance E, and followed by that, which is really just, based upon the shear force that's going to get generated in our flanges, multiplied by the depth. So again, that's really just this is just a moment divided by the shear force. And if we load here, then what we'll find out is that our section will go, so if we're loading right at E, I'll try to draw this 3D again for you. If we load right at E, well, then we actually end up just getting the section to translate and bend straight down. So hopefully you can tell the difference between this coming straight down and that one torquing. Now, this value E is really important because, we use a lot of channels in structures. And we call this distance the shear center. So if you load a section at its shear center, then you won't get any twist. And that's why, for symmetric sections, the shear center coincides with the with the location of the centroid. But for our asymmetric sections, that's not the case. Now, what's interesting, if we look at the channel and we turn the channel on its side, and we draw what our shear distribution, our shear flow distribution is going to look like. Well, it looks really very similar to kind of half of what the box section is, but we got to come back down to 0. So if that's what our shear force distribution looks like, shear flow, well, then if we look at what our forces are, and this is V sub F, V sub F, V sub W, V sub W. Because now we're symmetric again, all of the moments cancel out. So if we took our moments about the centroid, well, the distance here to here is the same. So we're loading about the centroid. So we have 0 twist was created by the this applied moment. These are equal and opposite and the same distance apart, and these are equal and opposite and the same distance apart. So we see that if we turn a channel, just by turning the channel on about its weak axis, we don't have this twist. So it really comes down to what the distribution of these shear forces are. As to whether you're going to have a stability problem. So that's really the essence of why we teach shear flow for structural mechanics, is really this twisting action and determining if it's going to be a problem. We'll look at just one sort of last little example, no numbers, not even really any free body diagrams, but you'll see just really to drive the problem home. Well, a lot of channel sections, particularly for thin wall, they'll put these little lips on the ends, and that just stops the edge from buckling. Well, the shear flow in those, because you've got a little bit of a little section here, you're going to go linearly, parabolically, and parabolically. So if we look at those forces, and I'm just going to draw them the same way as the as in the diagram here, just for simplicity. Well, you can see now the presence of these little forces. If we take a moment, you know, about this part, well, it's gotten even worse because now we have the contribution of these two little forces on the ends also wanting to make it spin around. So you find that here, with these channels with these little flanges, the E gets even bigger than for E here with a channel with no flange. So these are good to stop buckling, but the price that you pay for this, because there's no free lunch in engineering, is that your shear center increases. And so it's got if you're going to load it on the web, it has a lot more tendency to want to sort of twist. So that's going to wrap up our look at shear flow. And like I said, the key takeaway with shear flow and understanding how this shear moves around a section is not, the stresses are important, but really the direction comes into how we look at what the internal forces are on the section and how those internal forces are going to affect the stability of the section. And with that stability, it's really this concept of shear center. So how far or where you have to load your section in order to keep it from twisting so that it will just deflect down nice and straight. So that's going to wrap up our component or our little module on shear flow and shear center.